Hi, welcome back to this class on differential manifolds. I promised you that I would shoot a second video, and I think I will probably shoot a couple of videos because I think there are many questions, interesting questions, that indeed some of you asked me, and I want to answer these questions. Well, the first thing I'm going to do is to motivate more the importance of Poisson geometry, integrable system, and the connection to group actions. So I'm going to first use some slides in this video that I hope to be short. This is really the sequel of the former video, so please look at the video up there before this video, because this is a continuation. So now I'm going to share with you my slides. Okay, that's the previous slides. That's not what I want to share. Okay, sorry. All right. That's what I want to share with you now. All right. So I want to explore more deeply the connection of integrable system and group actions in this video, and especially to motivate with you I hope that you can see this properly, otherwise it will be a disaster. Now my computer is doing something strange. Let me double check. I'm going to stop sharing. 1 second. I hope that this works. Sorry, this is direct things. Share screen. There we go. Let's see if this works. Okay, perfect. That's what I wanted. Now you should see on my whole screen. No, that's the other one. All right, now it works. Okay, crash course on integral systems and moment map. Moment maps comes. The language again comes from physics. And I will finish these slides talking about moment maps, but I will give more examples after. Okay, so I want now to connect integrable systems to group actions, but I'm also going to start looking at these Poisson brackets in dimension, which is odd. So from the Poisson perspective. Indeed, that's my first example for you. Let's consider the determinants on R3. Okay, that's a very simple example. And now I want to consider, I have two functions, all right? I have two functions here, and I consider the system of differential equations described by these functions, where h and k are constants of motion, okay? The flow lies on h equal to constant and k equal to constant, okay? So that's, let's say, the dynamics, or if you want, that's the statement, that's the situation. I want to consider these equations. And I say determinants in R3, why? Because, well, in principle, where do you get the determinants? I consider the following brackets. I consider two brackets, f and g associated to h as the determinant of the f dg dh, and f and g associated to k as the determinant of the f dj dk. The interesting thing is that these two brackets satisfy that they are skew symmetric. That's obvious from the definition of determinant. They satisfy that they satisfy Leibniz rule, and they satisfy Jacobi identity. Okay. So that's interesting. Well, also here I didn't say, but they satisfy Leibniz. Leibniz is harder, okay? Because how do you check Leibniz? Then you check that the flow of these vector fields, this is what is a posteriori going to be the Hamiltonian vector field of the Poisson structure, because I use the same definition that I had, well, you don't see it very well here, that in the symplectic case, the bracket is just a Hamiltonian vector field of F. So for a general Poisson structure, I want the same situation. So that's, let's say, that's a motivation example coming from real life. And, well, it seems that this differential equation here, well, you can check it out, is the same as the differential equation given by the Hamiltonian vector field of H. Okay. One thing you can easily check is that you have this Poisson bracket equals to 0. So you have this kind of symmetries. You have two Poisson structures. This is indeed an example of bi-Hamiltonian vector field, which I will not discuss any further on this course. You can find this motivating example in the notes of the course. Okay. And that's a very nice example that I learned from Paul Van Aken. And indeed, it's an example of bi-Hamiltonian vector field when you have two Poisson structures that satisfy some compatibility equation. Okay, so this motivates a little bit considering Hamiltonian equations and considering integrable system from a perspective of Poisson geometry. That Poisson geometry, I will talk about this in some recorded videos that I gave some course in 2014. They are perfectly recorded, but they're professional. You know, there is a whiteboard, really a blackboard. For a mathematician, it's better to have a blackboard that you can read and you can follow, and it's great. And there are some notes, and you will have them in Atenea. So there's no way I can do this better than now with this whiteboard or with my notebook. Okay, so this will come later on. Now let's go back to the example of, again, examples where you have integrable system. Well, now I'm going to describe again the coupling of two simple harmonic oscillator. That's the example we saw. And we have an easier example if I look at rotations on the sphere. Okay, now I look at rotations on the sphere, and what I get here is the following interesting thing. This case is an example that I compute with the iPad the other day. I compute the partial of theta, okay, as vector field, and I was considering the symplectic form dh wedge d theta, and then I told you that when you contract the vector field partial of theta with this symplectic form, then you get minus differential of h. So rotations on the sphere are a perfect Hamiltonian vector field with Hamiltonian function the height. That's a perfect example. And an interesting thing that happens here is that this Hamiltonian vector field itself, I can think of this vector field, okay, as the vector field generated by a group action. Which action? Just rotations on the sphere. The action of SO2 on S2, but rotations on the sphere. This action that you have considered, and you have done several problems in the previous chapter, in chapter 3. Okay, I could try to consider this. And what do I mean by vector field generated by this action? I look at the orbits. The orbits of the action are going to be, by rotations, are going to be exactly the parallels of the sphere. And if I look at the vector field which is tangent to these parallels, that's the vector field generated by the action. Indeed, this is what is called the fundamental vector field. Okay, so here the fundamental vector field is partial of theta. Okay, and now an easy thing you can do is look at this case. Well, an easy remark from this picture here is that if you look at here I call it mu, and this is the moment map. That's the first example of moment map. If you look at the moment map, which is what? It's what is the moment map here? Wait a minute. It's just a function such that this Hamiltonian vector field coincides with the vector field generated by rotations. Do you see it? Okay, in this case, I only have one component. That's easy. And I look at the image of the height function, and I get a whole interval. And if I go to, this is in dimension 2, so I just have one function. If I go in dimension 2, and I have two functions, and I consider that this is an action generated by a torus, the torus here is one-dimensional. In dimension 4, it would be two-dimensional. A natural question is, what is the image of this moment map? Okay? And it will turn out, to your surprise, that it's a polytope. And that's a theorem due to Delzant, who is still alive. He's in Strasbourg. He's professor in Strasbourg. If I can link the webpage, I will link it here. Okay. And in his thesis, in his PhD thesis, he proved that when you have a manifold and you have an action of a torus such that all the generators are Hamiltonian, then the image of this action, the image of these first integrals of these vector fields, which you, let's say, you gather in what is called the moment map, the image of the moment map is a polytope, and it's a polytope with certain conditions, and it's a polytope of half the dimension of the initial manifold. And an interesting thing is that you can here connect differential geometry on a manifold with linear geometry on a space, on a vector space. And if you have two-dimensional polytopes, then you can also relate the linear geometry that you can do on one hand, reads on the other hand here as symplectic geometry. So it's a very nice, wonderful theorem. So, by the way, in particular, when I have this torus action, which I'm assuming is global, so it's a different situation from these action angle coordinates, because in the action angle coordinates, I know I have a torus action, but just defining a neighborhood of the Liouville toric. And here I assume I have a global action of a torus. So this is more restrictive, but it's a particular example of integrable system. And what's very interesting about this collection of examples is that by some strange reason, well, by not so strange thing here, they appear in algebraic geometry, and they are called toric manifolds. So they are also of independent interest for algebraic geometers. But now let's go back. Let's go back in business and recall that Arnold-Liouville theorem that I explained before is telling me that in a neighborhood of a Liouville torus, you have this fibration by torus. Here you have this fibration in the previous example by torus. The torus here are circles, and they fiber over the image, and they fiber so simply that really S2 you can reconstruct it just by gluing all the fibers in this ordered way. You can do also some more theory with these guys. Very interesting. Okay, so now if I go back to integrable systems where you have manifold symplectic dimension 2n with n first integrals that Poisson commute. The Arnold-Liouville theorem, or Liouville-Miner-Arnold theorem, is telling me that in a neighborhood of a torus, I just have one model which looks like this. Okay, I just have one model which looks like the Boo symplectic form. Oh my God, that's great. And that this is written in some coordinates that make sense in a neighborhood of a torus, not only in a point. These are the action coordinates and the angle coordinates that I can think of in the neighborhood of a torus. Well, you know the angle, and I understand that it's a coordinate in the sense that we all know that you need to have two covariance. When I say theta is a coordinate, all of you understand that what I mean is that the differential of theta is perfectly defined, right? Okay. Okay, so the characters of the day, well, I should also add here Emmy Nether, and maybe Michel Audin, why not? But here I have Liouville, Miner, Delzant, Arnold, okay? And Miner, as I recall, he gave this explicit formula for the action functions, and the Liouville one form of the symplectic structure makes sense in the neighborhood of a torus. Very good. Topology of the, so when you want to prove this theorem, so the sketch of the idea to prove this theorem is the first thing is to prove that when you have one of these torus, you, in a neighborhood, you will have torus that are aligned in this way. This means that in a neighborhood of the torus, my manifold is just the product of a torus and a disk, And the fibers of the disk are given by the second projection, by the projection of Tn times dn over dn. How do you prove this? That's interesting. One way to do this is using the exponential map. Is you take a Riemannian geometry, okay, and Riemannian geometry, okay, you take a Riemannian metric, and the exponential map, what it does for you is to linearize. Okay, you can take things to the tangent model, and you can indeed use this exponential map. You can cover by a finite number of balls and use this exponential indeed to prove that this is a vibration. You can also do this with an Ehresmann connection. Okay, indeed there is a proof of this in the notes. You can try to look at it. It's towards the end, and it's written indeed in the language of Poisson geometry, so it's done more generally than just the symplectic case. Indeed, that's a theorem we proved with Paul Van Akke and Camilo Angenu. All right. Now I need to introduce more material. I need to talk about moment maps, and I have given a hands-wavy definition at the beginning of this lecture, but now here is the definition. That's the definition. I have a group, compact Lie group action acting symplectically on a manifold. What does it mean? That they act symplectically means that the vector fields that are generated by this action are symplectic vector fields, so that the Lie derivative, that's something we saw in this video before, that the Lie derivative of omega is 0. All right? And now we assume that the action is not only symplectic, but Hamiltonian. Okay? And we say that the action is Hamiltonian if there exists an equivariant map. So we need to assume that there exists first a map that goes to the dual of the Lie algebra. And this, the first time you see this formula, you need to think about this. In the case in which the group is the torus, that's much easier. But here in this course, we have dealt with the general Lie groups. Why not? We could look at this definition. So if I look for each x, so if I have a mapping on the dual of G, I can make sense of it just by applying the image, because this is a linear, the set of linear functions on G. It makes sense just by when I pair this with an element of the Lie algebra. Okay, so I take an element of the Lie algebra x. Okay, and I compare mu, the image goes to G star, okay, and I pair it with x. And so mu x is what? Mu x is just a function, okay? And this function accounts for the ith component. So if I think that this is a torus, I can order these functions, okay? And then I have, and then I just have to, if I order these functions as such, okay, then I need to, sorry. Well, if I just order these functions, then what I'm saying is that the ith component, okay, is the Hamiltonian vector, is the Hamiltonian function for the vector field generated by this, because this vector field, this vector in G generates a vector field. Just how do you make this vector in the Lie algebra generate a vector field on a manifold? I have the exponential map. I take the exponential map. This gives me an element of the group, so it acts on the manifold, and then I take the tangent vector to this point, and at each point, this defines a vector field. Okay, so that's what it's called, the fundamental vector field of the action. Okay, that's quite intense definition. In this definition, we only need it in the Toric case, and in the Toric case, it's easier. You will see it in the next video. Okay, so I need to require that this is equivariant. When I say equivariant, it means that when I plug here the group action, which group action? The group action of G, it converts into a group action here. What is the group action here we are going to consider? The co-adjoint action. The co-adjoint action, you saw it in chapter 2 by Professor Eric van der Vaan in these videos here. But I will recall it in the next video just in case you forgot about it. Okay. So that's the definition of moment map. When this happens, we have a moment map. All right. Indeed, when the group is a torus, it's much simpler because the co-adjoint action is trivial. Okay. So this becomes the fact is saying that the action is, that mu is invariant by the group action, which is going to be automatic. So in the Toric case, this definition becomes easier. But in the general case, that's the definition of moment map. And it's interesting to give it in general because the word momentum, comes from the momentum in physics. And this is related to SO3, which is non-abelian. Okay, so it's good that I give the general definition. That's the definition of moment map. Okay, and moment maps and reduction that I will not study in this course provide an effective tool to study symmetries in problems in mechanics. Okay. So here, for instance, we can associate a toric action to an integrable system under some mild condition. Well, not so mild, because you need to assume essentially that you have global action angle coordinates. When you have global action angle coordinates, you have a global torus action, and then you have a toric action. Okay, so there are a lot of examples in which you cannot have this global torus action. But if you have a toric action, then that's the theorem I was talking about, the theorem of Delzant before, tells me that toric manifolds are just classified by the image of the moment map. And the image of the moment map is a polytope that has some interesting conditions among the edges and among the angle between the normal and so on, has some constraint. That's called the Delzant polytope. Okay, and the Delzant polytope is the image of the symplectic manifold. I didn't write it here, but I'm assuming the manifold is compact, otherwise this is false. Okay, so if I have a compact manifold, the image of this is just a polytope. In dimension 1, this is an interval. Example, rotations on the sphere that we saw before. In dimension 4, let me take for you CP2. Why not? Let's take CP2. Okay, I can take the complex projective space. And this is four-dimensional, if I think of this as a real manifold. Okay, it's four-dimensional. Therefore, if I can find an action of them, if I want to check that this is toric, I need to find a two-dimensional torus acting on this. And the torus action is given here below. T1 and T2 are components on, so I look at T2 as a product of two S1s, and T1 is a coordinate on one of the circles, T2 is a coordinate on the second circle. Okay, and these are homogeneous coordinates on CP2. Why not? Okay, and these acts in the following way: Z0, Z1, and Z2 are the four complex numbers. Okay, I can multiply with the exponential of A. This is a perfect toric action. I will explain this example in more detail. Why I will explain. I will focus more on. I will explain. Next video will be with my iPad. I will explain. Well, it's not an iPad, it's a Surface Pro, but I will explain for you in more detail things that I said in this video. But I think that maybe it's good for you to have more examples, which is what is the generating, what we call the fundamental vector fields of an action. Okay, and examples about moment maps, an example about Hamiltonian actions. Okay, and then after doing this, I will sketch for you the proof of Arnold-Liouville theorem, because once you know that the topology of the manifold, you have a fibration by tori, then what's going to be super interesting is that you use a Lie group action by a torus to check that you have actionable coordinates, and you use the Roux theorem. Do you want to learn more? Stay tuned and watch next video. See you later.